4 days after the flight, the aerospace world buzzed with speculation, theories, and analysis. The images of Starship breaking up during reentry had already gone viral. Critics questioned the reliability of the craft. Supporters doubled down on the necessity of rapid iteration. But amid the noise, SpaceX engineers were silent, buried in data. Hundreds of telemetry streams had been recorded from launch to disintegration, including heat shield sensor readouts, Raptor engine telemetry, guidance corrections, and internal system health diagnostics. What they found shocked even the most experienced engineers. The flight had not only provided insight into why the upper stage failed but had accidentally confirmed something SpaceX had long theorized but never observed: evidence of plasma flow disruption due to unexpected atmospheric interference. It turned out that during Starship's reentry phase, a phenomenon never seen before occurred. High-altitude shearing winds had triggered a resonance pattern across the heat shield tiles. This wasn't just turbulence. This was like a harmonic vibration, a ripple effect across the body of the ship that caused microgaps to appear between the heat tiles and their mountings. Those microgaps, invisible in previous simulations, allowed superheated plasma to enter behind the shield. This was the smoking gun. The revelation was that Starship didn't simply fail because of a propellant leak. It failed because it encountered a completely new atmospheric interaction at hypersonic velocity that had never been recorded in any other spacecraft. It wasn't a design flaw. It was new science. For the SpaceX team, this failure was gold. The team had feared the unknowns of reentry ever since Starship began its orbital tests. Unlike the space shuttle or capsule-based missions, Starship uses an unpowered glide, belly first, relying on atmospheric drag and orientation fins to slow its descent. But the surface area involved is enormous, and that meant more exposure to heat and pressure. While thousands of simulations had modeled tile flutter and expansion, none accounted for this resonance effect. Within 72 hours, design modifications were already in the works. A new mounting mechanism for the tiles was proposed, one that allowed for minor flexing and real-time adjustment in high-pressure flows. It would be inspired by biological systems. Think of it like goosebumps on the surface of the spacecraft, tiny actuators that could adjust the aerodynamic profile moment to moment. But the revelations didn't stop there. Another piece of flight data revealed a potential breakthrough. The Raptor engines had performed far better than expected, even under extreme conditions. When telemetry from the final seconds of the flight was analyzed, engineers found that the engines were still functioning nominally, right until atmospheric instability compromised Starship's orientation. That was a huge deal. It meant the issue wasn't engine reliability, something that plagued earlier versions, but guidance and control during high-speed descent. It also meant the Raptor V3S had finally matured into the dependable powerhouse Musk had envisioned years ago. Their efficiency was also climbing, nearing a specific impulse that rivaled theoretical maximums for full-flow staged combustion engines. The world had just seen the birth of a new standard in rocket propulsion, and it almost went unnoticed beneath the shadow of the explosion. Internally, SpaceX began preparing for Flight 10. And this time, everything would be different. The company decided to combine 3 experimental objectives into a single mission: revised heat shield design, upgraded avionics with predictive atmospheric compensation, and for the first time, an in-space maneuvering test designed to simulate orbital refueling docking. This final objective was especially critical, not just for Starship's ambitions toward Mars, but for NASA's Artemis program. If SpaceX could prove that Starship could link with a second vehicle in low Earth orbit and remain stable, the path would be clear for fuel transfers. It would mean Starship could be refueled in orbit, then slingshot to the Moon, Mars, or beyond. Flight 10, now scheduled for late summer 2025, became the most anticipated launch of the year. The FAA, after reviewing the data from Flight 9, granted SpaceX conditional approval for a higher launch frequency. That included additional orbital testing from the Starbase site in Texas, where the company had quietly completed the construction of a second launch tower. The new infrastructure would allow for back-to-back launches within the same 24-hour window. It wasn't just about convenience. It was about creating a rhythm of launches that could simulate the cadence needed for interplanetary missions, something never attempted before in human history. As the media speculated and space enthusiasts celebrated the upcoming test, a more curious development occurred. SpaceX had sent an internal report to several government and academic institutions, including NASA, the European Space Agency, and a select few physics research groups. The report included the detailed data on the unexpected atmospheric resonance discovered during Flight 9. It outlined how Earth's upper atmosphere, when struck at certain velocities and angles, could exhibit plasma wave interactions previously only modeled in theoretical physics papers. This wasn't just a rocketry problem. It was a physics discovery. For the first time, aerospace testing had produced real-world evidence of an exotic atmospheric condition. And that meant other nations, those building hypersonic weapons, orbital delivery vehicles, or advanced spaceplanes, would need to rethink their models. SpaceX, in failing, had unknowingly taken the lead in an entirely new frontier of atmospheric research. Elon Musk, in a rare and unexpected X post, commented on the findings. When you try to go fast enough and high enough, nature doesn't just push back, it sings. Flight 9 taught us to listen. It was poetic, cryptic, and oddly reverent. But it summed up the mood inside the company. This wasn't just about landing rockets anymore. It was about understanding the invisible layers of our planet in a way no one had done before. As preparations for Flight 10 ramped up, the public perception of Flight 9 began to shift. Where once there had been disappointment and criticism, now there was curiosity. Journalists began referring to it as the plasma flight. Documentaries were announced. Academic conferences scheduled special panels to discuss the new resonance phenomenon. Suddenly, a failed test flight was being compared to Galileo's first look through a telescope, an accidental moment of clarity that changed everything. And perhaps the biggest revelation of all came not from SpaceX, but from NASA. In a quiet but meaningful announcement, the agency confirmed that if Flight 10 succeeded, it would greenlight a formal contract extension for SpaceX's human landing system. That meant Starship wasn't just a contractor's project. It was becoming a core piece of humanity's return to the moon. What had begun as an ambitious private project was now intertwined with the government's roadmap for the next 20 years of exploration. Starship Flight 9 had exploded. That much was true. But in its fire and failure, it had burned away more than just tiles and steel. It had revealed the boundaries of what we knew and what we didn't. It had told the world that when we reach beyond the Earth,